Welcome to this week's CAM Colloquium. It's a pleasure this week to introduce Michael Langberg as our speaker. Michael did his PhD work at the Weizmann Institute of Science in Israel and did a postdoc at Caltech. I guess I was also visited Caltech for a while. He's taught at the Open University of Israel. He now teaches at SUNY Buffalo. And I think he's done a lot of very nice work kind of at the intersection of CS and electrical engineering. So he's trained as a computer scientist, now is in the EE department and working on problems that maybe traditionally considered electrical engineering problems, namely network information theory. So I think some areas where we've had impact: index coding, the problem at the intersection of the two fields; network coding, which I guess Michael has shown is really kind of the same thing in the end; adversarial communication models, and recently he's been looking at how ideas from CS complexity theory in terms of problem classes and their relative hard disk can be applied. That sort of thinking can be applied to communication problems, specifically network information theory problems. So anyway, it's a pleasure to have Michael here. Okay, Michael.
So the title is sort of a reductionist view of network information theory. I hope it'll be clear pretty soon what that means. And I was told in multiple instances that the audience here is very diverse. So the talk is, I planned it sort of a high-level talk. I'm not going to dig into almost any technical details. I do have sort of prepared some technical details if we have time. But feel free to ask any questions and interrupt me in the middle. The goal is to do something that'll be understandable to the audience. So I want to talk about network information theory. And in this field of study, one would study communication networks and try to understand how to communicate over these networks and at which rates one can communicate, and I'll define this shortly. And this is a very rich and very intriguing field of study. There's been a lot of progress in this field in the last 50, 60, 70 years since information theory started out with the works of Shannon, but I think it's fair to say that there are a lot of problems that are very, very open. So just to mention a few problems, one could think of communicating over a network in which links of the network do not have any noise. This would be called network coding. Understanding how to communicate over these networks and at what rate to communicate is not very well understood these days. One can take this one step further and try to communicate over networks in which links are noisy, not noiseless, and maybe there are other components that are noisy, that are slightly larger components, maybe broadcasting components that are noisy. This is completely out of reach at the moment. So it seems out of reach, and the reason that it's out of reach is even very small, limited components with 3, 4 nodes are not well understood in this field of network information theory. And more. So you can think of communicating in a secure fashion, communicating against adversarial jammers. All these things are completely, or many parts of them are open. So a lot of problems are open, and the studies of these individual problems, of course, they're all talking about communication, so they share analytical techniques, but to some extent, they're very individual. So each problem has its own theory and its own sort of group of researchers that look at that problem. So the goal of this talk in general is to maybe suggest some kind of unifying theory that may explain why problems are common and sort of extract the commonalities between different problems. So that's the goal towards a unifying theory. And so again, individual studies that focus on specific problems, that's what we do every day, and this is extremely productive. I want to take a different perspective. I want to take a conditional perspective of network communication problems. And conditional meaning I don't want to focus on individual problems, I want to focus on connections between different problems. I want to relate different communication problems through the lens of reductions, which is a very well-known and simple tool. So if I have a communication problem N1 and I want to solve it, I can focus on N1, or I can try to connect it to another problem, say N2, in such a way that solving problem N2 would give me a solution to N1. So I want to relate between different communication problems. And reductions are a very, very simple tool, but the great strength of reductions is that I can connect between two problems even if I don't know how to solve either one of them. can still connect between them. So that's the idea. And I want to talk about reductive studies in the context of network communication. Reductive studies are very common. They're the bread and butter of computer science, cryptography, complexity theory. But I think it's fair to say that in other fields of study, the study of reductive connections between problems as a theme in itself is not very developed. So this is trivial for, I think, most of the audience, but I'll still say this. Why study reductions as a theme? So of course, if I have a problem, and that's sort of the most direct reason to study reductions, if I have a problem and I reduce it to an easier problem in such a way that solving the easier one will solve my problem, then I've turned my problem into an easy problem, I've solved my problem. But also reductions can show that a problem is hard, in the sense if I take a hard problem and reduce it to my problem, such that solving my problem will solve the hard problem, now my problem becomes suddenly hard. It allows the propagation of proof techniques, of course, between problems. And the study of reductions as a theme, and not just as a tool to solve something, it raises new questions that are not common in this field of network information theory. So it provides a framework, just like in complexity, to take the family of all different communication problems and maybe connect them together, cluster them together. These could be interrelated problems, and in such a way have like a taxonomy of network communication problems. And this also gives rise to, just like completeness in complexity theory, to identifying special problems, and we'll see one of them in this talk, that are interrelated to many other problems, and in a sense they're central to the field. So this can help, in general, unify and steer future studies. So that's the theme of this talk. And over the last, I think, 5 or 6 years, this has started catching on pretty strongly. And there have been many reductive connections between problems that, again, both of them are not solved, but reductions have been emerged. I'll just say a few words. So we'll talk, network coding is communicating over a network, and index coding, we'll see this, I hope, in the talk, if I'll get to it, and I think I will. So connections between network coding and this different notion of communication called index coding, connection between network communication, again, index coding, and wireless communication using something called interference alignment, connection between, again, communication and storage, and many, many other connections, which I won't sort of get into in detail. So what I want to do in this talk is discuss some of these connections. I'm going to focus on network coding, which is communicating over networks with noiseless links. And I'm going to focus on one problem that I want to say that's sort of like a central problem, which is called the edge removal problem. So that's the plan. And again, feel free to ask if there are any questions. So what I'm going to do now, I'm going to sort of define the model of network coding more precisely. I'm going to get to the edge removal problem, and I'm going to compare it to a number of different problems, or related to a number of different problems. So I'm talking about communicating over a network. Again, I'm calling this network coding, and this is an instance of the network coding problem. We have a directed network. We have a bunch of vertices that generate information, these source vertices. We have a bunch of vertices that want to receive information, these terminal vertices. And we have like a matrix of requirements saying which source is required at what terminal. So we have like a matrix saying if SI is to be transmitted to TJ, then the IJ entry would be 1, otherwise it would be 0. So that would be an instance of the problem. And the objective, of course, is designing some kind of flow of information over the network that satisfies all the requirements. So I'm going to make some simplifying assumptions. Some of them I'm going to change throughout the talk, but just to have common ground. I'm going to think of this network as an acyclic network. So there's going to be some directionality between the sources and the terminals. So you can think of flow going, in this example, from top to bottom. Each edge is going to have a certain capacity. So we're going to limit the number of bits I can communicate over this edge per time step. Most of the talk I'm going to consider sources that have completely independent information. So there's no correlation necessarily between sources. They have independent information. This will change a little bit in the middle of the talk. And again, for most of the talk, I'm going to consider the communication scenario in which I have a bunch of sources, a bunch of terminals, and each source is required at just one terminal. So there are going to be SI-TI pairs. SI wants to communicate to TI, and that's all. That's the communication set. So it's called a multiple unicast. Okay, so I have a network which is multiple unicast. SI wants to communicate to TI. The links here are capacitated, and the network is acyclic, and there's no noise on the links. And I want to say that a certain rate vector R1 to Rk is achievable. Each Ri corresponds to a source Si. So this rate vector is achievable over this instance. And I'm also specifying the block length of communication, which corresponds to the time, the amount of time I'm communicating over the network. And I'm specifying the error that I'm allowing in my network communication. So this rate vector is achievable over the network with block length n and error epsilon if I can assign random variables, Si for the sources and Xe for each and every edge, such that the following hold. So each source is just going to be a random variable which is independent and uniform in such a way that its rate, its entropy, this is the binary entropy function, its entropy would be just Ri times n, which essentially means, and I'll jump ahead a little bit, that each Si is just a one uniform message out of this 2 to the power of Ri times n messages. That specifies the rate of source Si. So that's Si. Each and every one of them are independent, and we'll revisit this independence later. So SIs are these random variables. We're going to have random variables XE for each edge. XE is going to be a random variable for each edge. E is capacitated the edge. So I want this random variable to have support of CE times n bits. Again, n is the block length, so I'm going to have support C times n, which means that my support of the random variable is a subset of size 2 to the power of C times n messages. So I have these random variables, S for the sources, X for the edges. I want to say that these random variables correspond to communication over the network, which means that there's some kind of flow of information going over the network. Essentially, this means that each and every edge, the random variable on this edge is a function. So the random variable XE is a function FE of the incoming random variables. So for each edge E, FE is a function of all the incoming random variables. We do this in this case from left to right, from all the sources up to the terminals. So yeah.
Can you clarify again the meaning of XB? I'm trying to find an intuitive interpretation of it. So I understand that every edge has a capacity C sub E, and there are n time intervals. Right? So that's where C sub E times n comes in.
Yes.
Why are we taking 2 to the power C sub E times n?
So thanks for the question. I encourage questions. The intuition is as follows. We're communicating over the network. We're allowing n time uses of the network. The network is acyclic, so you can think of the messages being vectors of Ri times n bits, which is a message in this set of size 2 to the power of Ri times n. And now, once we have messages of the sources, let's say these are the sources, they're communicated to some node, and now this outgoing edge, which is a random variable Xe, is a function of these incoming information. The number of bits I'm communicating over this edge is going to be now C times n, which means that I can represent a set of 2 to the power of C times n different messages on this link. Did that help?
So I'm not talking, we're not recording the status of the edge at all instances in time. That's not what's going on, right? I misunderstood that.
So essentially, you can think of this, just for simplicity, because of the acyclic nature, think of this as using every edge just once, maybe. And sort of the information is starting at the sources and sort of flowing through the network. Each time we're communicating over an edge, and each time we're using exactly C times n bits over this edge. You can take that kind of communication and stream it, and then you'll have like a stream of information going through. But it's easy to capture this as just being a one-time use of each edge.
But isn't the time component completely lost in this? I'm asking very naive questions, but I'm probably
that's
as
fine.
much into this as there
So
is
the advantage of the time component is that you're allowing yourself, your elements that you're communicating are over a larger alphabet, which means that you have more richness in your encoding functions. You're allowing yourself to encode functions over a larger alphabet, which gives you more power.
So one of the values of X and E is all possible messages which could be passing together throughout all time through that specific edge.
Definitely, yes.
Got it.
Okay, good.
Sorry.
Thanks. Okay, good. So this information is flowing through the network, and the terminals are getting some kind of information they want to decode, and each terminal is going to decode to some potential SI, let's call it SI bar, and we're going to say that communication is successful if all the terminals decode correctly. So we want communication to be successful. We have this error parameter epsilon. We want it to be successful with probability 1 minus epsilon. In this entire process, the only randomness, or let's say each and every function here that defines the encoding is a deterministic function. So the only aspect of randomness is what messages are actually transmitted by the sources. So we want, for a 1 minus epsilon fraction of source information, we'd like this communication to be successful. So if communication is successful with probability 1 minus epsilon and over block length n, we're going to say that this rate vector is epsilon n feasible. We're going to use this terminology throughout the talk. Or we're going to say maybe epsilon n achievable. And if for any error epsilon there exists some block length n such that I can communicate with block length n and error epsilon, I'm going to say that this rate vector is just feasible. So I can obtain this rate with any epsilon that I want. I can take the error to be as small as I want. And the notion of capacity is a very common notion. Information theory just takes the closure of the all feasible vectors. Okay, so that's the setting. This is how I want to define communication. Now I want to define one problem that I feel is a canonical problem in this field of network information theory. This is the edge removal problem. It was defined by Ho, Frost, and Jalali, I think something like 5 years ago. And it's the following very, very simply stated problem. So I have a bunch of sources, a bunch of terminals. I have a multiple unicast connection. And I know, for example, that I can communicate at this rate, R1 to RK, over the network. So I can communicate at that rate over the network. This means that for arbitrary small error, I can communicate the sources with this small error if I take a block length which is large enough. And this network has some edge E, and this edge E has some capacity. Let's call the capacity of the edge, let's call it delta. So I'm thinking of these edges as having a capacity delta because I'm thinking of the capacity as being small. So I assume that rate R1 to RK is achievable over the network N. I'm asking myself, what can I say regarding the network N after I remove the edge E? So that's the problem. I know I can communicate a certain rate vector over the network N, and I'm asking myself, what can I say now regarding the network in which I change it just by a little bit? I just remove the edge E from the network, and E could be maybe an edge of very small capacity. How much did this rate vector change? So what can be said regarding the achievable rate on this new network? Or in other words, what is the worst case guarantee in my loss in rate when I'm experiencing link failure? That's sort of the question, yes?
So it's not, like it could also be the most important edge failing.
Yeah, it could be, it's a worst case edge in a network. The thing is that it has just delta capacity, and think of delta as being small. It's a parameter, but think of it as being small. So what is the loss and rate when removing this delta capacity edge? And it's pretty easy to see that when you're removing an edge, you're losing rate. You're losing your ability to communicate. That's clear. But you could also come up with examples in which you're going to lose a rate of delta additively in each and every component. So removing one edge is going to remove delta rate from each and every component. So I'll show a very simple example, and it's essentially called the butterfly example. So if you haven't seen the butterfly example before, it's actually a nice example, just a nice communication problem. So I have this very simple network. S1 wants to communicate to T1, S2 wants to communicate to T2. All these are just, let's say, allow one bit of communication over the network. So I want to think of block length, for example, 1. And so I can communicate S1 to T1 and S2 to T2 in a very simple manner using the following scheme. So I can obtain rate of 1, 1, meaning 1 bit from here to here and 1 bit from here to here, by the scheme that S1 sends out its information, S2 sends out its information, and on this bottleneck link, I encode the information to the sum of S1 and S2. And now terminal T1, because it has these two, it can decode the original S1, and T2 can decode S2. So this is a nice example where mixing information inside a network is strictly stronger than just routing the information in the network, because if you would route, you can show that you can't satisfy both S1 and T1 and S2 and T2 because of this bottleneckage. So I can obtain rate 1, 1 on this network, and now the question is, if I remove an edge of capacity delta, how much can I obtain? So let's make an edge here of capacity delta, so I'm going to turn these middle edges into 1 over delta edges, each one of capacity delta, so it still remains capacity 1, essentially. I'm sort of breaking it down to small fractions. And I'm removing one of them. And now it's not hard to see that if you remove one of them, then the best rate you can get is 1 minus delta from S1 to T1 and 1 minus delta from S2 to T2. The reason being that now if you sort of remove this 1 minus delta amount of edges here, you're disconnecting S1 and T1 and disconnecting S2 and T2. That's called a cut set bound. So based on the cut set bounds, you can at most get this rate. And actually this rate is achievable. You can actually achieve this rate also. So removing this delta capacity link, reduce the rate in each coordinate by delta. That's what happened. And the question is this the price of edge removal in general? So is it true that any network is going to allow me to, if I remove this edge of capacity delta, can I still communicate at the original rate, but just minus delta in each coordinate? That's the question. And this is sort of a formal statement, which is not known to be true. It's not known to be false, which just says what I just said previously. Let delta be larger than 0. Any network coding instance that's R1 to RK feasible with network N with this edge E of capacity delta is this R1 minus delta up to RK minus delta feasible if I remove this delta from this edge E from the network. So that's the edge removal statement. And again, it's not known to be true or false. It's completely open. You'll understand how open it is in a second. But it's known to hold. Yep.
Here's something with the formulation, actually. So if a node has multiple outgoing links, is it required to send the same signal on every outgoing link? Or can
No.
you choose different signals for each link?
You can choose different signals.
In the butterfly example, each node sends the same signal on all of its outgoing links. But that, in general, that doesn't have to happen.
Yeah, in the butterfly example, it's a very simple example, so that's sort of the optimal solution, but yes.
Okay.
So it turns out that for a bunch of special cases, it is true. This edge removal statement is true. And one such special case is called the multicast case, in which if I have all my sources co-located at one single location, and all the terminals want all the information of all the sources, this is called multicast. In this case, it's true that if I remove this a small link in the middle, it's going to affect my capacity or my rate by just a small amount. So I remove a delta capacity link, I'm reducing rate by delta. The same happens if all the sources are co-located, and the terminals may want, each terminal may want a subset, a different subset of the sources. So this also holds. Even in this case, it holds that if I remove a delta capacity link, I'm affecting my rate by at most delta. And if I'm communicating over my network with codes which are linear, so you can think of these encoding functions at each internal node that take information and give me an outgoing information, if they're linear, then in this case also, if I'm removing a delta capacity link, I can prove that you can still communicate at high rate, at this rate R1 minus delta to RK minus delta. And again, the question is this true in general for all network coding instances? And you can even ask a relaxed question, a simple question, which says, this is very rigid. I'm removing delta, and I want to lose at most delta. But you can think of an asymptotic kind of version in which I'm removing delta, but my effect is some function of delta, some f of delta. And the only important thing is that when delta tends to 0, when this edge that I'm removing tends to 0, then I would expect the effect on the capacity to also tend to 0. So what I'm saying is if I can communicate at rate R1 to RK on the network N, then when I remove this delta capacity edge, I want to communicate at rate R1 minus some f of delta, RK minus some f of delta. But this f can be like 100 times delta, 1,000,000 times delta, the size of the network times delta, 2 to the power of the size of the network times delta, anything, as long as f of delta tends to 0 when delta tends to 0. So even this asymptotic intermodal statement is not known to be true. Yeah, it looks like it should be known. It's not known. Maybe I'll say a word about what the difficulty is in a second. So it seems simple, but it's currently very open. So we're talking about edge removal in noiseless networks. I want to give some examples of edge removal in noisy networks, or examples in which edge removal does not hold in noisy networks, which may give intuition why a very low rate edge may give a lot of benefit in communication. So for noisy networks, edge removal does not hold. And this is known. And here I'll give 2 examples. One example is adversarial noise. So think of point-to-point communication. I'm communicating from X to Y. I want to send n bits over this communication channel. I have a jammer that's, let's say, can flip a p fraction of the bits. So this is an adversarial kind of noise setting. And to do this, to communicate in this setting, you want to use error correcting codes that have large minimum distance. So that's point-to-point communication. I'm going to change this a little bit. And I'm going to add, if this is n bits, I'm going to add a channel of log n bits, a very low rate channel. But now, when I want to communicate between X and Y, I can instead of using an error correcting code that allows unique decoding over Y, what I can do is I can use an error correcting code that allows what's called list decoding over Y, in the sense that I'm sending X is being corrupted over the channel, and Y is not able to decode to a single word, it's able to decode to a list of code words. And I promise myself that one of the code words is inside this list. And now once I have a list at Y, and I use this very low rate side channel, I can send like a hash or a signature of the information that was transmitted, and this way Y, out of this list that it gets, it can disambiguate and get a single value. The thing is that there's a significant difference in rate between uniquely decoding over an adversary and list decoding over an adversary. So what happens now is, if I remove this edge, I actually can lose a significant amount of rate, although the edge is negligible. It's only log n bits for a block length of n, which means its capacity is log n over n, which is something that tends to 0. Yes?
Is that weak link also subject to adversary attack, or that one is actually error-free?
That's an excellent question. So in this very simple model, I'm making it error-free. I'm also making it hidden from the adversary. So I really think of this as like an isolated channel that the adversary sees what's going on here and can affect this guy. It doesn't see this and it can't affect that. That's a good question. So for adversarial noise setting, removing even a very low rate channel is going to can affect rate quite a lot. And you can also come up with examples for memoryless noise. So this is called a multiple access channel. We have one input x1, another input x2. They go into a channel. There's some kind of stochastic nature of this channel, probability of getting y when given x1, x2, and y is the output, and based on y, you have to decode x1 and x2, and you use this channel over multiple uses of time, and eventually, if you use it at n time steps, you'd like to sort of decode after these n time steps. But each and every time step is completely independent. So this is the memoryless noise model. It's very well understood and studied a lot. So we alter this just a little bit and add what we call a cooperation facilitator, which is a node which can receive both x1 and x2, do some computation, and then sort of whisper a little bit of information back to x1 and x2 at a very low rate. Again, very low rate. This could be of rate of n bits, and this could be like log n bits. And it can be shown again that if you communicate without this cooperation facilitator, without these links, you get a certain rate. You just remove these links from the network, and suddenly the rate. I'm sorry. If you communicate with the cooperation facilitator, you get a good rate, and you remove these links, the rate sort of drops significantly. So it's not continuous in the sort of capacity of these links. So that's for noisy networks, and we're in the noiseless case. And in the noiseless case, as I said, it's not known what the price of edge removal is. Is it asymptotically significant, or is it asymptotically negligible? And so both the statement and this relaxed statement is not known. And maybe I'll just say a few words about why this is difficult. So you can think of having a network with this edge E and having a communication protocol over this network. And now suddenly this edge E disappears. So there are nodes on the other side of the edge that depend on that information to continue their process. But using an averaging argument, because this edge may have very low capacity, you can sort of maybe guess the best value on this edge and treat that value as the value that would have been communicating over that edge. Maybe you'll just lose a little bit. And that strategy works, but the problem is that given your source information, you want to sort of correlate between the sources that eventually give you this value on that edge. And this is a difficult task because the sources are independent. I think that wasn't clear based on the faces that I get from the audience. So the challenge is, given a code on a given network, if I want to show that you can still communicate at a good rate without that edge, I have to sort of design a network code on the network without the edge. So the edge is now not present. And now I have to do something. I have to sort of massage my first code into a second code, and that seems very difficult. Yeah.
So how is it that you're able to surmount this challenge in all those cases where this thing is known to be true, like linear and the multicast and so on?
So in the co-located source case, when the sources are co-located, so that's sort of what I was hinting on in the previous argument. If you think of communicating over this network with the edge, then just look at the value that was communicated over this edge. It's one of not too many values because the capacity of the edge is very low. So I can maybe assume that the edge is communicating the most common value. And I'm not going to lose much because I sort of divided by that too much. So I say that if the communication actually gave me that specific value on this edge, forget about the edges. The node afterward would say, okay, as if I got a certain value on that edge. The thing is that I have to correlate between the sources in such a way that eventually on this edge, I'm going to get that value. And in general, I cannot correlate between my sources. So in the co-located case, I can correlate because they're all co-located. And in the linear case, there's enough structure to sort of find some kind of uniform distribution, but over some linear subspace that does allow this correlation. So, yeah.
So if you have the edge that the receiving edge of the removed edge and the receiving node of the removed edge, that one now after the edge is removed receives delta times n less inflow, or whatever we would call it. What if it's just randomized over the possible bits that would have been on those delta n pieces of information or bits of information? Then, like with some probability, it would get it right, which it would be not a high probability, but as delta goes to 0, that probability, like the
Yeah, but
number of
even-
bits
even-
over which you would have to randomize would become small.
Yeah, so even if think of the link as being just a 1-bit link. So either 1 was communicated there or 0. And if you're guessing, that already gives you a probability of half of being in error. And you want to sort of, your notion of communicating is allowing a communication scheme that sort of gives you a correct decoding with probability tending to 1. So
Okay.
if you have more than 1 bit, if the number of bits depends on n, so it's exponentially decaying probability of success. Okay, so we don't know if it's true, we don't know if it's false. It's a very interesting problem to look at on its own. But nevertheless, what I want to do here, and I'll try to do this in 20 minutes, I'm going to have to shorten things a little bit, is to study the implications of this problem as if we know if it's true or false. And it turns out that this problem has many implications. So it has implications on reliability problems on network communication. It has sort of implications on cooperation, or the benefits of cooperation in network communication. There's some implications on what kind of topological structures are good or not good, and also the demand structure is connected to this problem. So it has many connections, and what I'll do now is I'll talk about reliability, and I think I'll jump afterwards to the notion of topology, and because I won't be able to go through all of them in the time that I have. Okay, so let's jump to a different problem and see that it's connected to this edge removal problem. So this is the 0 versus epsilon communication problem. That's how I call it, and here's the problem. I have, again, a multiple unicast network. K sources, K terminals. I'm communicating over the network, and I know that I can communicate at rate R1 to Rk if I allow myself a little bit of probability. So if I allow myself probability tending to 0, as long as it's not 0, then I'm able to communicate at this rate R1 to Rk. But now I want to insist on communicating with 0 error. Not with epsilon error, but with 0 error. What can I say? So what is the cost in rate that I have to pay when I go from some small error, which could be negligibly small, to an error which is 0, that is always communicating correctly no matter what the source information is. So can one obtain a higher communication rate when allowing an arbitrary small error as opposed to 0 error? And there are many examples outside of the world of network coding in which, yeah, if you allow a little bit of error, you get a significant benefit in rate. So this is a famous problem, the Sapien-Wolf problem. I have 2 sources, x1, x2. In this case, they're dependent and not independent like one would expect in network coding. And I have these capacitated links, and I'm asking myself, can I communicate x1, x2 over these capacitated links such that y can decode both x1 and x2? And if I'm allowing a little bit of error, then I can do this with certain capacities on the links. And if I'm allowing no error at all, then suddenly I cannot do this completely. I would have to have links of very high capacity to communicate to y. So there are settings in which there's a clear benefit between epsilon error and 0 error. But we're asking the question in network coding, when the information is independent and these channels are noiseless. Okay. Question. So is there any advantage in epsilon error versus 0 error for general network coding? And I'll say what's known. So this is, again, the epsilon error or epsilon versus 0 error statement. It says that for any epsilon, if I have a network coding instance that's feasible with R1 to Rk rate with an error of epsilon, then if I insist on 0 error, I'm going to get R1 minus delta and Rk minus delta, where delta is some function of epsilon, and delta tends to 0 as epsilon tends to 0. So in words, if I'm able to communicate for any epsilon larger than 0 at a certain rate, then I should be able to communicate with no loss, essentially, at rate 0. So I get continuity at this point of 0. And we're in the same setting. So the multicast setting is a very well-known setting in network coding for people that have sort of seen network coding. And the optimal schemes given there are actually zero error. They're optimal in the sense that they're the best you can do even with epsilon error, but they're zero error schemes. So this statement is true trivially, given the previous works on multicast communication. Again, this is the setting in which all the sources are together, all the terminals want all the information of all the sources. This co-located source case in which the sources are together but the terminals want different subsets, it turns out that this statement is also true. It's a more involved proof. And again, if you have linear codes, it's actually enough that the encodings are linear, the decoding can be any function, then again the statement is true. So you're not gaining anything by allowing an epsilon error. And we're asking once more if the statement is true in general. Which again says that is this loss in weight continuous to the function of epsilon? So that's the 0 versus epsilon error problem. And the thing is that you can connect edge removal and 0 versus epsilon error. So it's kind of a nice story. I was working on edge removal. I was sure that edge removal, or that my gut feeling was edge removal is true, in the sense that removing a delta capacity link should only affect the network with delta capacity. We don't know this, but that was my gut feeling, and I was working on this 0 versus epsilon error problem. And again, the gut feeling was the opposite, in the sense that there must be a network in which allowing a little bit of error will boost your capacity. And so I was right and wrong at the same time, and it turns out that edge removal is true if and only if this 0 versus epsilon error is true. So the edge removal problem, you're losing a delta capacity, a delta element in capacity if you're moving the edge of capacity delta, if and only if there's no advantage in epsilon versus 0. So I have slides that sort of give this kind of proof, but I won't go to it. You have to do two directions. Edge removal implies 0 error implies edge removal, and at least the slides that I have, and which I can show maybe offline if someone's interested, is you sort of assume that you have a network which is feasible with epsilon error. You're assuming the edge removal holds, and you prove that you can actually go to 0 error with some negligible function delta of epsilon. So you get this. This is one direction. That edge removal actually asymptotic edge removal implies epsilon versus 0 error, and the other direction you can also prove. And then for the other direction, you don't need this. You get something stronger. You don't necessarily need the asymptotic version. But okay, these are details. So you can connect between edge removal and 0 error, and that's sort of one of the connections of edge removal. So that's one of them. If I know edge removal, I can understand also the connection between 0 versus epsilon error. And I want to show a few of these connections. So it depends on how much time I have. I think I'll jump a little bit ahead. So I won't do this connection, which is, I'm sorry for that. I'll do this. So again, I want to connect edge removal to a bunch of different problems. Here's a problem on topology that's related to topology over networks. So recent studies have shown that any network coding instance can be turned into something called an index coding instance, in such a way that if you solve the index coding instance, you can solve network coding. So there's a reduction taking network coding to something called index coding, which I'll define in a second. And you can go back in the sense that if you solve this index coding instance, you can get a solution to network coding instance. So we've seen what network coding is. What is index coding? So index coding is also a network communication problem. It's an instance of network coding, but a special one, in which each and every terminal wants, again, just the information of its corresponding source. SI is to be communicated to TI. But these TI gets two kinds of information. One information is kind of a broadcasted information. So there's a broadcast link that takes in all the information of the sources, broadcasts some capacitated version of them, of some encoding of them, and broadcasts this to all terminals. So they get each terminal gets something that all terminals get, and it also gets something called side information, which is direct information from the sources. And so index coding is one type of network communication that seems to be pretty useful. It's useful, for example, using a video on demand. So you can think of a server as having all these different movies. Each user wants its own movie. Each user has bits and pieces of previous movies that they have seen. And based on these bits and pieces of previous movies they've seen, the side information, the server is going to schedule a broadcasting scheme that's going to satisfy all the users. So, and this is actually in use, actually in practice, in emerging technology for video on demand. So, there's an efficient reduction connecting network coding to index coding. And this is conceptually a simpler kind of instance of network communication. And I want to maybe explain why I think this is a little bit simpler. It captures all of network coding, but conceptually it's simpler. And the reason being that network communication in general, I would view it as something challenging because it combines two different notions. One is topology, these topological connections, and the manipulation of information. So I need to manipulate information based on the connections that I have. So I'm combining these together. I have to take into account when I'm manipulating information what information I have, the combinatorics of it. And in index coding, the thing is that there's just one node that does encoding. And this node has access to all the source information. So in a sense, we're separating topology from information. There's no topological constraints on encoding, and all I need to do is I can manipulate freely, but I need sort of to satisfy the decoding. Okay, so there's a connection between index coding and network coding, and this connection could be sort of phrased in the following manner. A network coding instances are feasible if and only if its corresponding index coding instance is some R prime feasible for R prime is equal to a certain specific function f. So I can characterize feasibility here based on feasibility in the index coding. And this is called sort of a reduction in code design, in the sense that a code for the index coding world will give me a code for network coding. But in the information theory community, it's common to ask a very related question and ask not only what rate is achievable, but you would like to maybe ask what is the capacity of these networks. So the capacity, again, of a network would be sort of the closure of all achievable rate vectors. So we're just adding this closure operation to this connection. And it turns out that just adding the closure operation sort of breaks this reduction down completely. So if I want to understand what is the closure of all the achievable rate vectors of this network, using the closure of all achievable rate vectors of this network, I cannot do that anymore, even though I have this nice connection between them. And very roughly speaking, the reason is that the dimension here of the geometrical region, these vectors, differs from the dimension here. This is efficient reduction, but it still blows up the dimension. And so it actually matters how you approach things, and this is the reduction is very delicate in that aspect. So people, including myself, have tried to sort of fix this reduction in such a way that it not only allows to design codes from one place to the other, but actually can be used as an oracle for this capacity region. So it turns out that if you try to fix this, then you're actually solving, again, the edge removal problem. So edge removal is going to be equivalent to the following question: can you determine the capacity of network coding given the capacity of index coding instances? So if edge removal is true, you can do that, and if edge removal is false, then at least this reduction will not allow you to do that. So again, here edge removal sort of came up in a natural manner. So we've seen connections between edge removal and zero versus epsilon error, between edge removal and capacity versus code design. It depends on the feeling. So should I start converging? Or because you said with questions?
10 minutes.
10 minutes? Ah, okay. So I'll do one more connection, and then I'll sum things up. So I want to connect edge removal to this issue of network demands that we haven't talked about too much, but we'll talk about now. So if I have a communication network, we said that we were sort of assuming that SI wants to communicate to TI only. That's called multiple unicast. That is, SI to TI is a sort of a unicast connection, and we have multiple such unicasts. But you can think of more elaborate connections in which SI maybe wants to communicate to a bunch of terminals, and SJ wants to communicate also to a bunch of terminals. There could be overlap. So a completely general setting. This is called multiple multicast. And in general, multiple multicast is harder than multiple unicast because it's a more general problem. So people connected multiple multicast and multiple unicast, and this started with network coding in a very limited setting of zero error. It went through linear index coding. There was a connection between these two. And at some point, we have a connection for network coding, for index coding, for any network, any noisy network. We can say that if I get a noisy network that's sort of this kind of black box that has a multiple multicast flavor to it, one source can be wanted at multiple terminals, I can sort of reduce this using some gadgets to a multiple unicast network in which each source is wanted by just one terminal in such a way that solving the second problem gives me my problem. Okay, so that connects multiple multicast to multiple unicast. And there was like one step, beautiful work a year and a half ago that takes it one step further and says for network coding, I can go from multiple multicast to multiple unicast, but from multiple unicast I can actually go to two unicast. So two unicast completely captures all of network coding. In the sense that I can take any network coding problem, I can add a gadget around it that has just two sources and two terminals. Source 1 wants to communicate with terminal 1, source 2 with terminal 2, and that's it. And solving this is going to give me a solution to the previous one. The thing is, and this is very strong, it's sort of amazing that for two sources you can capture all of network coding. The thing is that this held in a very limited setting of zero error, so it was very combinatorial, the proof. And again, it worked in code design and not in this more general framework of capacity, which is the standard framework studied in information theory. So you would like to determine the capacity of network coding using these two unicast networks. And just as before, the reduction completely breaks down when you add this notion of capacity. And you can connect this to edge removal in the sense that you can show that doing this is going to solve edge removal. So the connection is the following. You can show again that if the asymptotic edge removal statement is true, then you can determine any network coding or the capacity region of any network coding instance by the capacity region of just a very structured instance of two sources and two terminals. And the opposite again is true, that if you can determine this using the reduction presented, then again, edge removal statement is true. So we went I wanted to show 4 connections. We showed 3 of them. In general, I'll say it again. So edge removal, understanding edge removal, gives understanding of a bunch of these different problems. And there's sort of a meta-theorem that's arising by looking at this. And the meta-theorem says the following. I have a model of communication, which is communication over networks, let's say over a given network with the way I defined it in the first slides of the talk. And I'm changing this model slightly in many different kind of aspects. And it turns out that these changes are all equivalent to one another. So they either affect the model or don't affect the model in the same way. And the changes were, do I want an epsilon error or do I want a zero error? Do I want to talk about really achieving a rate or do I want to talk about approaching a rate? We didn't see this about dependence, but we can ask, am I talking about communicating over sources which are completely independent or communicating over sources which are slightly dependent? That also is equivalent to edge removal. And again, adding an edge of negligible capacity or not having this edge. So all these forms of slackness are kind of equivalent to one another in the sense that they all either affect the capacity region or don't affect the capacity region So there are more connections, and I'm going to jump through the next slide because I don't want to waste too much time. But there are even more connections that removal, and it really is turning out to be a central problem. Okay, good. So that's essentially it. I wanted to talk about this paradigm of reductive arguments, and I focused on the edge removal problem, which again is an open problem which is related to a bunch of different problems. I feel that it highlights the central nature of the edge removal problem. And I want to stress that these connections were revealed because of a study that focuses on studying reductions for sake of reductions and not studying reductions for the sake of solving problems. So this kind of reductive paradigm is what gave rise to these different connections. And I mentioned, and I won't get into these details at all, there are a bunch of other connections that are have arisen recently, and they do give some kind of flavor of a partition of the space of problems where something is starting to emerge. So that's essentially it. Thank you.
Questions?
Yeah.
You mentioned earlier that you were using tools from theoretical computer science in information theory. And is that exactly what you meant to some extent? That the reduction paradigm, which is something that, like in theoretical computer science, is very prevalent, that this is being introduced to information theory and is a new tool that didn't used to be used then?
Yeah, so this is in our lunch conversation. So I was saying that part of my sort of research is connecting themes that are common maybe in computer science and plugging them into information theory. So I wouldn't say that reductions aren't used. Reductions were used and are used. It's a very natural tool. They're used quite a lot, but they were used as a solution. So I want to solve a problem. I suddenly discovered that I can use sort of in a black box manner a bunch of other solutions and I can solve my problem. But they weren't studied when I sort of to connect between problems that no one has any idea of how to solve them. They weren't studied to sort of give a structural kind of view of the field. So this is exactly what I meant. So taking complexity and turning it into information.
Yeah, I had some questions. Is the edge removal problem solved for any network coding instance for which the capacity region is unknown? Or is the answer known only in cases where we actually know the capacity region fully?
So in the linear case, for example, it's known that if I'm, I'll say for scale linear, but in multiple unicast, when you're communicating with linear functions, in some cases it's actually an NP-hard problem. So it's not known. It's not known. I'm tempted even to say that even if you restrict yourself to linear functions, it's not even known to be decidable if a certain rate vector, because you can't limit the alphabet size, if a certain rate vector is achievable or not. But still, edge removal holds in these cases. So there are cases of edge removal in which the capacity is not well understood at all. There are probably not instances. So if you're looking for a counterexample to edge removal, it probably does not exist in places in which the capacity is known. And these are, well, there are not too many cases actually. So network coding is really completely open, so almost nothing is known explicitly.
Thank you.
Okay.